Hello there, Mr. Sutton here, bringing you this Pre-Cal Honors 4-1 lesson on exponential functions. In this one, we will be learning how to graph exponential functions, also how to write exponential functions if we have an a and a b value, more on that later, and as a real-life application, we can model things such as population growth. We'll do a little exponential function graphing to warm us up here. So complete this table and then graph the function. Pause the video and take a sec to do that. All right, going through each of these x values, we've got 3 to the negative 1. That is 1 over 3. So this is getting plugged into the exponent part of this each time. 3 to the 0 is 1, 3 to the 1 is 3, and then 3 squared will be 9. I'm going to make my grid lines go by 2's just to make sure I can fit everything. So we've got negative 1, comma 1/3 somewhere over here, 0, comma 1, 1, comma 3, and 2, comma, let's see, 9 is going to be all the way up here. And connect the dots. Now, as you're doing this, make sure that you're approaching but not quite hitting the x-axis, because as we'll see in a sec, we do have a horizontal asymptote there. Now that we've graphed one of these, let's just get a quick overview of exponential functions. So we have this standard exponential form. All exponential functions can be written as some number times some other number that's being raised to a variable. This is really what makes it an exponential function, is having this variable in the exponent. Now these letters actually have different things that they do for us, and we could have ab to the t, same thing. The a value is going to be the y-intercept. If you plug in 0 for x, you're going to have b to the 0, which is just 1, it goes away, and you're left with the a value. So you can always tell what the y-intercept is by looking at that number out in front. B is going to be our growth factor. This is the number that we multiply by over and over and over and over as this exponent gets higher and higher. Now, if the b value is bigger than 1, if you're multiplying by a number that's bigger than 1 constantly, you're actually going to have growth. So this picture I have right here is an example of exponential growth. If, on the other hand, b is between 0 and 1, you're going to have decay. If you're multiplying by, say, 1/2 over and over and over, your function's going to be getting smaller and smaller, and you'll end up with a graph that looks like this. So it's the same graph, really, just kind of reflected over the y-axis. Now, you might wonder why I didn't just say b less than 1. Well, if b is less than 0, then you don't even have an exponential function. You can't return negative values either. You can't input negative values for the base, and we can't return negative values back. We can't even return 0. It doesn't matter if you have a positive number, it doesn't matter what exponent you raise it to, you're never going to get 0 or negative out of that. So as I said on the last page, we do have a horizontal asymptote at y equals 0. Now some of you might be wondering, well, why can't we let the base be negative? The short answer is because we can't. That's just not something you do with exponentials. Slightly longer answer, if you have a negative b value, you're sometimes able to plug in fractional exponents like the 1/2 power. We don't want to have b to the 1/2 power, because that would really be the square root of b, and that would give us imaginary numbers. So that's why we're not allowed to have negative bases. Let's take a look at a real-life exponential problem now. The element ninium, it's a made-up element, but it decays at a rate of 9% an hour, let's say. If 34 kilograms are present now, find the amount present 3 hours from now. All right, so we're going to start this. First off, we know it's an exponential problem because we're growing or decaying at a certain percentage per time unit. This is our tip-off, it's exponential. So we can start by writing our standard exponential form, and I'll write this as f of t equals ab to the t. And I'm using t instead of x because we're talking about time now. So now I have to figure out what a, b, and t are. Let's start with a. A, we said, is our y-intercept. In real-life terms, that's going to be our starting value for the problem. So they said 34 kilograms are present now. That means 34 kilograms will be our a value. For the b value, this is what you're going to multiply by over and over and over. And this is going to involve your percentage that they're giving you. So in order to figure out what we have to keep multiplying by to lose 9%, well, losing 9% really means you've got 100% and you're losing 9% from that, right? So that's like 91%. So what does that mean as an actual number to multiply by? Well, 100%, a percent really means divided by 100. So 100 minus 9%, that's really like having 1 minus 0.09, which is 0.91. 91%, 0.91, same thing. So that's the number that we're going to multiply by each time. Now, at this point, you could also figure out t, but I'm going to pause for just a sec, just to collect and show you what we have. We've got 34 times 0.91 to the t power. This is a function that I can plug any amount of time into, and it'll tell me how much ninium is left. So let's figure out the t value. You have to be careful with the time units. This 9% is an hourly rate, and they said 3 hours. So we're going to plug 3 in here. Don't assume the time units are always going to be the same, but this time they are. So plugging in 3 for our time, this is now a calculator question. So I've entered 34 times 0.91 to the third power, and here's the exponent button in case you forgot. Enter. That's going to be about 25.62 and some change, and that's going to be kilograms. Now, since this is decaying, just as a sanity check, this should be less than what you started with, and it is. Here's another real-life exponential function. Try this one on your own. All right, let's see what we came up with. So price of a video game increases 13% of a year. Current system costs $600. How much was the newest system 5 years ago? Starting with our exponential formula, A value, that's the current price of the system, $600. The B value, this is what we're multiplying by each year. Now, if we're increasing 13% each year, that means that we have 113%. So that's going to be 1.13. And we want to know what the system was 5 years ago. So let me first write just my exponential function with the t still there. We're going to have 600 times 1.13 to the t power. And now 5 years ago, this is where you have to be careful picking your t value. 5 years ago means we're going back in time 5 years. So we need a negative t value. So this is going to be 600 times 1.13 to the negative 5 power, which we will now plug in the calculator. And that's going to come out to $325.66 approximately. And going back in time, hopefully the video game systems do cost less, at least, if you go back in time. So there we have it. One of the most common exponential problems in real life is half-life problems. Just to give you a quick look at the scientific term, half-life is how long it takes to lose half of something. So for example, the half-life of radium is 1,600 years. If 8 kilograms is present now, how much will be present in 900 years? So the way that we can set this up, we could try setting this up with the standard model. We could say, okay, 8 is my A value. That's how much I have now. What am I multiplying by each time? Well, it's half-life. If I'm losing half of something, I'm multiplying it by 0.5. And then we don't really know what to do for the exponent, but let's just suppose we put t in there. So if we had 8 times 0.5 to the t power, would this work? Well, the way this works, if t is in years, every single year you're going to multiply by 1/2. Is that really what we want to do? Not really. We're supposed to multiply by 1/2 after 1,600 years. Not every single year, or else we're going to run out of radium very quickly. So the setup that we have for our exponent isn't quite working here. We need to set up our exponent so that we wait a certain amount of time before multiplying by 1/2. And the way we can do that is using a fractional exponent, like so. So if we have our half-life formula, f of t equals ab to the t over k, what this is going to do, you're going to wait k years before you actually get a whole number for this exponent, which means it's going to wait 8 years before multiplying by 1/2. Now, you can plug in fractional exponents to your calculator, so you don't actually have to wait 1,600 years before you multiply by 1/2. Obviously, this thing is decaying in the meantime, but using this setup will let us do it on the calculator. So let's tackle that problem again, this time using our half-life formula. So again, 8 is our A value, half is our B value, 0.5, and then we've got a certain number of time. K value is going to be 1,600. The K value here, you're always dividing by whatever amount of time you're supposed to wait for the b value to take effect. The t value now, the time, is going to be 900 years. So we'll just put 900 in that fraction, and then let's let our calculator do the work. And just a note, when you're doing this, on a lot of calculators, you're going to need to use parentheses for those fractional exponents. It all depends on whether your calculator has that fancy thing where it puts whatever you do in the exponent in its own little special box. Or if you have to do what I'm doing on my calculator right now, if you have to do this craziness and use this little hat thing for your exponent, then you're going to need a parentheses to make sure that all this stuff in the exponent stays together. So pressing enter, we've got about 5.42 kilograms of radium left over. Try this next problem on your own. We have a population of rats quadrupling every 3 months. If there's 200 to start with, write a formula for F, the population, after t months, and then how many will we have after 18 months. Pause the video, give it a shot. Now the trick on this one is this is actually a half-life problem in disguise. The reason it's a half-life problem is we don't want to multiply by, let's see, quadruple means 4, right, times 4. We don't want to multiply by 4 every single month. We want to multiply by 4 every 3 months. So we'll have an A value of 200, that's our starting value, B value of 4, and then we're going to make this t over 3 because we want to multiply by 4 every 3 months. Next, plugging in 18. Let's let our calculator figure this one out. So 200 times 4 raised to the 18 over 3rd, or 6th power, comes out to 819,200 rats. That's a whole lot of rats. Oh well, that's too bad. So we've got two different types of formulas, AB to the t and AB to the t over k. The big question is, how do we know which formula we need to use? Take a sec to think about this, and we'll put our heads together. So the real tip-off here is you need to use the half-life formula if you don't want to multiply by your growth factor every single time. If you need to wait a certain amount of time before multiplying by b, you use the half-life formula, t over k. Now technically, you could use the half-life formula for everything. Normal situations, you've really just got a k value of 1. If you want to wait 1 time unit before multiplying by the b value, then you could still use t over k. So you really could think of it as just being one formula, but k is 1 in these normal situations. Well, that's it for exponential formulas. Until next time, this is Mr. Sutton signing off.